Recording started.
Okay, so this meeting is being recorded, and that comes in handy, especially for people who are unable to make it at this time. My name is Professor Houston, and I'm one of the math instructors that teaches MAT 115. And if you have a question, there's a couple of things you can do. There's a chat button. If you click on the chat button, then you can type questions in that chat box. That's really a good way to be able to, type in your questions. And if you need to hear audio, of course, if you can hear me, then all is good. But I did type in the chat box about how you need to call in. Okay, so I'd like to get started with just talking about what we're going to be looking at this evening. And with the reasoning, we're going to spend the first half on reasoning and the second on problem solving. So let's go ahead and get started. And I will pause every once in a while to see if there's any questions along the way. Okay? So, I just wanted to mention, you're not going to need to feverishly write down everything that you see on the screen, because this file, my file that I'm using tonight, I will post. If you're my student, I will post it in Blackboard. If you are another instructor student, that's not a problem, because I will be emailing this file to all the MAT 115 instructors, and also at the same time, you can always email me and I'll reply back with the file. So there's that option as well. Okay, so we're going to spend the first half going over inductive reasoning. In the second half, we'll be looking at Polya's method of problem solving to solve real-world problems, which is basically the two main things that you see in the Chapter 1, Homework 1. Okay, so inductive reasoning, this is where you take a specific example and draw a conclusion from it. Many times, inductive reasoning conclusions are drawn from looking at patterns. The good news about this type of reasoning is that all you need are specific examples. And so, and then you can, from those examples, go ahead and draw conclusions. So let's look at a couple of examples that this works with, that we're going to be looking at the pattern. Some of your, and what I tried to do is pick examples that resemble your homework problems so that it would help. Some of your homework problems deal with successive differences. So we're going to use the method of successive differences to determine the next number in a given sequence. And and so here is the list of sequences, and want to know what number comes after the 82. So we have 7, 2, 4, 13, 29, 52, and 82. So to begin, we ask what number was added to arrive at the next number. That's how we're going to start. Now, just by looking at the 7, 2, 4, 13, 29, and so on, you can't really tell a pattern just from that. So we're going to take a look at what's happening in this pattern. So on the next screen, you'll see that we're looking at what we're adding to the first number to get the second number, and so on. So I have 7 plus a negative 5 is 2, and then 2 plus 2 is 4, and 4 plus 9 is 13. So I'm looking at my row here, and this second row is basically I'm listing the numbers that I add to get to the next number. Now, when you're doing this method of successive differences, you keep doing the process until you get a whole row where all the numbers are the same. And since this second row contains all different numbers, we have to keep going with this process. We can't just stop here. Because right now, I still don't see a pattern. And so we're going to do this again, and we're going to look at what do we take with the first number and add to get the second number. Well, negative 5 plus 7 is 2, so there's the 7. 2 plus 7 is 9. 9 plus 7 is 16, and so on. So if you notice, that whole row, the third row, are all 7s. Negative 5 plus 7 is 2, 2 plus 7 is 9, 9 plus 7 is 16, and so on. And since we reached a row that has all 7s, since it's all the same number, we can now determine the pattern, and we can take a look at what would come to the right. Well, I know that this next number would be a 7, since that's the pattern. And so I would take 30 plus 7 and get 37. So I know the next number in the third row is 7. The next number in the second row is 37. We can continue this way and figure out what comes after 82 by taking 82 plus 37. 82 plus 37 is 119. So we are able to figure out that the next number in the pattern is 119. Okay? So we were able to take a look at the pattern, figure out what number comes next. So when you're doing the successive differences, you want to just keep writing down what you add to get to the next number, and then you keep going down the row, first row, if you don't get the same number, then you got to do it again, and you keep doing that until you get a row where all the numbers are the same so that you can continue the pattern. Okay, let's take a look at another inductive reasoning type problem. Find the sum of, and then there's 1 plus 2 plus 3, all the way up to 500 using this particular formula. Now, you may think, why can't I just find the sum, 1 plus 2 plus 3 plus 4, and just add it all up? Well, I'm going to address that in a minute. But for now, let's take a look at using this formula. This formula, n times n plus 1 over 2, is how we're going to find the sum. So the key is that number n. The variable n represents a number. And the n represents the number of numbers that I'm adding. And I'm adding 500 numbers together. So that means n is 500, which means n plus 1 is 501. So what we're going to do is take those numbers and just substitute them into the formula. And that gives us 500 times 501, and then divided by 2, 125,250. Now, back to this whole typing the 500 numbers into your calculator, because I know someone was thinking that. Why would we not want to do it that way? Well, there's a good chance you can make a fat finger mistake. That's where you just accidentally type the wrong key, or you could skip a number, because you're counting from 1 to 500. It's easy to make a mistake in skipping a number or counting the same number twice. So really the easiest way to do this problem is to use the formula. Okay, let's take a look at another problem. Predict the next multiplication fact in this list. So we have some rows of multiplication equations. 37 times 3 is 111, 37 times 6 is 222, 37 times 9 is 333, and we want to be able to write what equation comes next. So there's 3 numbers in each row. We're going to take a look at the pattern of what's going on in each of those numbers to see what we would write next. So the first number is always 37. In every row, the first number is 37. So in my answer, the first number is going to be 37. And the second number notice, is multiples of 3. I'm going to go back. I have my second number is right here. Notice those are multiples of 3, 3, 6, 9. So the next number in the pattern would be 12. So here's what I have so far. My first number is 37. My second number is 12. And notice I just brought down the multiplication symbol and the equation symbol. So let's take a look at what happens on the right side of the equal sign. That's the third number. Well, each of those 3 digits are all being increased by 1, so I would end up with 444. If we take a look again back here at our problem, the third number in the problem, I have 111, 222, 333. It makes sense that the next row would have a 444. So it looks like this is going to be the next row in the pattern. 37 times 12 equals 444. And you always double check that the left side equals the right side. Yes, it really is true. Now, in my math lab, sometimes they have you write out the entire row. Sometimes they have you just write out part of that last equation. But if you have to write out the entire row, please remember to use the multiplication symbol that's next to the problem for times. Because the X on the keyboard, my math lab does not read the X on the keyboard as multiplication, it reads it as the letter X. Even though they look the same on the screen, my math lab reads them differently on how you type it. So 37 times 12 equals 444 would be the next row in that pattern. Okay, so let's do another one. Follow the pattern to determine what would be the next equation. So it's kind of like the one we just did. But I wanted to do this one just because it does have a little bit of a different take to it. You know, they're not all going to be exactly the same. So I have 1 equals 1 times 1, and 1 plus 5 equals 2 times 3, and 1 plus 5 plus 9 equals 3 times 5. And so that's what we're looking at, and we need to look at the pattern on the left side of the equal sign and then look at the pattern on the right side of the equal sign, kind of like what we did in the last problem. So what I did is I just wrote the numbers on the left side of the equal sign, because we know they're all going to be plus signs. That's all we have on the left side is plus signs. But let's take a look at what's happening with the numbers. The first number is a 1. The second number is a 5. The third number is a 9. Now, if we're going to continue this pattern, it looks like we are just continually adding 4 to the list. So it looks like the next number would be 13 because we're continually adding 4. So on the left side of the equal sign, I think we're going to have 1 plus 5 plus 9 plus 13. So let's look at what's happening on the right side of the equal sign. These are the numbers. On the right side of the equal sign, let's see what kind of pattern we have. Well, actually, I'm going to look at each one of these columns separately. This column has a 1, 2, 3. So following that pattern, that means the next number would be a 4. If I take a look at this column, that's 1, 3, 5. So continuing in that pattern, the next number would be 7. So let's take a look at what this would be. So the first column is counting by 1s, like I just mentioned. So it looks like we would have a 4 next. The second column is counting by 2s, so it looks like we would have a 7 next. So we put this all together. The next equation in the pattern would be 1 plus 5 plus 9 plus 13 equals 4 times 7. And then always double check to see if it is correct. If we take the left side, we get 28. If we find the right side, we get 28. So they match. The left side does equal the right side, and this equation right here seems to be following the pattern that was set for us in the problem. Okay, so let's take a look at another kind of inductive reasoning situation. This one is kind of like one of the multi-step ones you have in your homework, where it says, choose any number and follow these steps. Okay? We're going to multiply by 2, and then we're going to add 6, and then we're going to divide by 2, and then we need to subtract your original number. And then we're going to write down the answer and see what happens with the answer and see what kind of pattern comes up. Okay? So let's try this with the number 2. I multiply by 2 and I get 4, add 6 and I get 10. Okay, so I took my 2 times 2 and that gives me 4, and then I add 6 to that, which gives me 10. Then the next step, divide by 2, gives me 5, and then you subtract your original number. Well, when I subtract 2, that gives me 3. So when doing this process, starting with number 2, I end up with the answer of 3. Okay, so let's see what happens with a different number. Let's try this with 5. So the same process, multiply by 2 gives me 10, add 6 gives me 16, divide by 2 gives me 8. Subtract the original number is 5, so my answer is 3. Well, that is the same thing that we got last time. Let's try it with another number and see what happens. Multiply by 2 gives me 22. So I start with 11. Multiply by 2 gives me 22. Add 6 gives me 28. Divide by 2 gives me 14. Subtract the original 11 and I get 3. I do notice a pattern here that I keep getting the answer of 3. And when you're doing this type of problem in the homework, it's going to give you, you're going to end up getting the same answer a lot of times. The ones I was looking at, a lot of them were that way. So let's see what's happening if we just let the original number be n, to just pick a letter. See what happens. When I take n and I multiply by 2, I get 2n. And then I add 6, gives me 2n plus 6. And then I divide by 2, which gives me n plus 3. And when I subtract the original number, that's n plus 3 minus n, which is 3. So this is a pattern here showing that no matter what number you start with for n, you're going to end up with the answer of 3. So doing it with the variable x or n, whatever variable you want to pick, you can pick y. If my math lab says to pick n, then you need to pick n. And you can go through this process to show that you will always get 3. Okay, so this is just saying yes. When the same process is followed, the result is 3 each time. And but what we did with inductive reasoning is we started with specific examples and then went from there to draw a conclusion about how the result should be 3. Okay, now some more inductive reasoning type questions were the Gauss method in adding up numbers. And I know that this is some of these problems that talk about using this method you know, can cause students problems. So I wanted to make sure we covered the Gauss method. Okay, so Friedrich Gauss, very smart individual, came up with a way when he was actually a child to add a list of numbers very quickly. His teacher gave him this assignment to try to keep him busy, and he was done in no time at all because he noticed the pattern. And if you look at the list of adding up the numbers 1 through 100, you can pair up numbers and get 101 each time. The first number plus the last number gives you 101. And then the second number plus the second to the last number gives you 101. And then the third number plus the third to the last number gives you 101, and so on. So we could just keep pairing up numbers. We know that the sum is always 101, so if we know how many pairs we have, then we can just quickly find the sum of the numbers. Well, there's 100 numbers in this list, and if you pair them all up, that's 50 pairs. So the middle pair is, 50 plus 51, which is 101. There's 100 numbers in the list. That's an even number of numbers. They each get a pair, and that's 50 pairs, and each pair adds up to 101. So there are 50 pairs of numbers that add up to 101, and when you multiply those together, you get 5,050. So the sum of adding the numbers 1 to 100 is 5,050. So something that could have taken a very long time, especially if you're going to do this by hand and not with a calculator, actually didn't take that long at all if you use this method. Okay, so now I know in the homework they throw you some other like curveballs related to this. So let's try another problem using the same technique. We'll find the sum of 1 up through 181. Now if you do the same idea and take the first number plus the last number, you get 182. And then if you take the second number plus the second to the last number, you get 182. Third number plus the third to the last number, 182. So we're going to pair them up this way, and each pair adds up to 182. Now, this is a little bit different than the previous problem we just did because there's 181 numbers. 181 is an odd number. So if you pair up all the numbers, you're going to have one left over. And so we need to figure out what that number is and also figure out how many pairs of numbers do we have. Well, if we look at the first 180 numbers and we pair those up, then, or like the 2 plus 180, 182, 1 plus 181, that's 182. How do we got to find that number in the middle number is actually 91. And the easy way to find which number is the middle number is you just take the sum and divide by 2. So the sum is 182, divide by 2 gives me 91. So that's a quick, easy way to find what the middle number is. So I have 181 numbers in my list. There's an oddball number, number 91, but the rest, there's 180 numbers left, and you pair them all up, so that's 90 pairs, okay? So I have 90 pairs adding up to 182. And then the middle number in the list, we just tack that on. So 90 times 182 is the sum of all the pairs. You add the 91, which is the oddball left over, gives you 16,471 for the sum. Again, this is a lot easier than taking the first, 1 plus 2 plus 3 all the way up to 181 to get the 16,471 as the total. So you have to, it makes a difference whether you have an even number of numbers in your list or an odd number of numbers in your list, because if there's an odd number of numbers, there's going to be a number that's left out, and you have to find that number. Okay. Let's do another example. of using Gauss's approach. In this sum, I have 4 plus 10 plus 16 plus 22, all the way up to 58. This one's a little bit different than the previous problems. First of all, it doesn't start with 1. The other two problems started with 1. And then also, I'm not counting, each number is not one more. I'm actually adding 6 to get to the next number. 4 plus 6 is 10. 10 plus 6, 16, and so on. So we have to work this one a little bit different. We still need to determine how many numbers are in the list. We need to figure out, is there an even number of numbers in the list? Is there an odd number of numbers in the list? We're going to take a look at a pattern to figure this out. So I have first term is 4. And then the second term, I take 4 plus 6. And then I take 4 plus 12 to get the third term. And then I take 4 plus 18 to get the fourth term, and so on. So it looks like I'm taking 4 plus a multiple of 6. And if you notice, the second term is 6 times 1. The third term is 6 times 2. The fourth term is 6 times 3. So there's a pattern there that n, if you let n represent the total number of terms, then it's 4 plus 6 times n minus 1 right there. And we're writing this equation so that we can find n, so we know how many terms there are in the sequence. I have to know, is it an odd number of terms? Is it an even number of terms? How many pairs do I have? So we need to figure out the n. So I take that equation and I solve for n, distribute the 6 here, and then I take 4 minus 6 to get negative 2, and then I add 2 to both sides, and that gives me 60 equals 6n, so n is 10. So that tells me a couple of things. It tells me, one, that there's an even number of numbers in the list. It also tells me I'm going to have 5 pairs. Okay? And we can actually use this to find the other terms in the sequence. We know the first, second, third, fourth, and 10th term already. That was provided. We could even continue on and find the other terms if we wanted to. The fifth term would be 4 plus 6 times 4. Sixth term is 4 plus 6 times 5. Okay, the pattern here is that, of course, that's n minus 1. So fifth term, that's a 4 there. For sixth term, that's a 5 there. For seventh term, that's a 6 there, and you can keep going on and on. So we could actually find all 10 terms. So we have a good idea of what this list looks like. We have 10 terms in each, so there are no leftovers. There's 5 pairs, and if I take 4 plus 58, notice I get 62. If I take 10 plus 52, I get 62. If I take 16 plus 46, I get 62. So we're dealing with the pairs adding up to 62, and there's 5 pairs, so the sum is 310. So like I said, this one was a little bit different because we had, did not start with 1, and the numbers were jumping up 6 at a time. So we had to look at it a little bit differently, but we still need to figure out how many terms total that we had. Okay, so on to the second half of tonight's webinar, and this has to do with Polya's problem-solving technique. Now, these 4 steps made this guy Polya very famous. It's so simple, but it's so applicable to so many things besides just math problems, and that's partly why we're still studying it today. These 4 steps, really important. First thing, understand the problem. You can't solve it unless you understand it. This may mean you read it over a few times. This may mean that you look up some vocabulary words that you don't know. So that's the first step. Second step, devise a plan. Figure out how you're going to solve it. And then the third step is to actually carry out that plan. And then the fourth step is to look back and check. And that's a really important step, because if your answer doesn't make sense, it doesn't check in the situation, then you did something wrong and you need to go back to the drawing board. Now, let's say your answer doesn't make sense, or you get stuck as you're carrying out your plan, you don't really come up with an answer. I want to emphasize it's okay. I think one reason why people get stressed out about like word problems, for instance, is that you get the idea that you need to be able to solve it right away. And that is not always the case. Your first answer is not always your best answer. You may not always have the correct solution first time around. Polya emphasized that if your answer does not make sense or you don't come up with an answer, it's okay. All you have to do is start the steps over. So it's not a failure to get stuck. It's not a failure to have an answer that makes no sense. It's not a failure. It's just the fact that you need to go back and try again. Okay? So there's your encouraging words for the night. All right. So let's do a problem where we're following these steps. I have to find the ones digit of 2 to the 4,000 exponent. So that means I'm going to multiply 2 times itself 4,000 times. And the ones digit is the number that's farthest to the right in that number, whatever that really long number is. It's a really big number. It's the digit that's farthest to the right. So let's follow Polya's steps. The ones place will be the digits farthest to the right, and that is understanding the problem right there, his first step. I'm understanding that I need to find what that digit is farthest to the right if I were to take 2 and multiply it by itself 4,000 times. Now, the second step is to come up with a plan to do this. I might be tempted to think, just do it on the calculator. The problem is 2 to the 4,000 is so large that your calculator would have to round and put it in scientific notation to give you the answer, which is not going to tell you the ones digit. So the calculator is not going to be helpful here at all. So let's come up with another plan, maybe like looking at a pattern. Okay, so we're going to try to look at some patterns. So step 3 in the problem-solving process is to carry out the plan. So we're going to look for some patterns. And I notice I'm dealing with exponents with the 2. So let's see what happens with exponents with a 2. I have 2 to the first is 2, 2 squared is 4, 2 to the third is 8, and then it keeps going. I did 2 to the fourth, 2 to the fifth, 2 to the sixth, and so on. Now, all we really care about is the ones digit. Those are the numbers here on the right. That's all this problem is asking us to look at. So the other numbers I can kind of ignore and just see what's happening with the ones digit. So I've just listed here the ones digit, and I notice a pattern, 2486, 2486. And if you take a look back here, you'll see it starts off 248, and then 6, 2486, 2486, 2486, and so on. So it looks like I have this pattern of 4 numbers that keep repeating itself. So looking for a pattern seems to be a good idea in this situation, and I just need to figure out the last digit of where the 2 to the 4,000 exponent ends up in this pattern. Okay? So the 2486 keeps repeating, but how do I know where this 2 to the 4,000 will end up in that rotation of 4 numbers? Well, let's look at the exponents that we're dealing with here. When the ones digit is a 2, I have in my list the exponents of 1, 5, and 9. Okay? Well, 5 divided by 4 is 1 remainder 1. 9 divided by 4 is 2, remainder 1. And I'm dividing by 4 for a reason, because there's a pattern of 4 digits that keep repeating. Okay, so my remainder is 1 for both of those, where the 1's digit is a 2. So it looks like I'm onto something here. Let's try and look at another one of these. When the 1's digit is a 4, my exponents are 2, 6, and 10. Now when I take 6 divided by 4, I get remainder 2. 10 divided by 4, I get remainder 2. Again, I'm dividing by 4 because the pattern is a list of 4 numbers, okay? When the 1's digit is an 8, the exponents are 3, 7, and 11. When I divide by 4, my remainder is 3 for each of those. So it looks like if I know something about the exponent, looking at it dividing by 4, looking at the remainder, I'll be able to tell what the 1's digit is. So if the 1's digit is a 6, the exponents are 4, 8, and 12. When I divide each of those by 4, I get no remainder. So it looks like the key is to divide the exponent by 4 and examine the remainder. That seems to be the connection. So if I take my exponent of 4,000 and divide by 4, I get 1,000 with no remainder. What situation is that? That's right here. When my exponent had no remainder when divided by 4, the 1's digit was a 6. So that tells me 1's digit is a 6. Okay? So if we look back, step 4 is to look back and answer. Look at the answer. It does seem reasonable that the exponent would be a 6. If I got an answer like, I don't know, -3, that just doesn't seem to make sense, right? So you want to look back to see, does the answer 6, does it seem reasonable? Yes, it does. So it looks like that's the answer we're going to go with for the 1's digit up to the 4,000 exponent. With practice, Polya's problem-solving process will come naturally, even for solving problems in real life. There's 4 steps. I'm going to go back to the 4 steps real quick. Go back here, right here. Understand the problem, devise a plan, carry out the plan, look back and check. The more you go through that process, the less you'll think about it, and it'll become more second nature. And if you think about it, these 4 steps are not just for math problems. They're for any kind of problems. Problems of real life being thrown at you, and you have to figure out what to do, okay? Now, of course, devising a plan for real life might involve more time in prayer, might involve seeking wise counsel. Devising a plan step is very important because you're going to try to get it right the first time. But as you know, life doesn't always bring you the same types of problems. You can't just use the same strategy for every problem that comes your way in life. And the same thing is true for the problems that you see in your homework. You can't just say, oh, well, a pattern worked for this one, finding 2 to the 4,000, so we'll use a pattern to solve all of them. Well, it doesn't work that way, and you know that life isn't that way. So the fact that, you know, in the problem-solving part of this homework, you're thrown with just different types of problems all mixed together is actually more true to life and realistic. So another little tidbit of encouragement, I guess, there for you. So let's work some other practice problems so we can practice the problem-solving process. The total revenue for a movie is $54 million. Each theater screen shows the movie averaged at, showing the movie averaged $60,289 in revenue. Estimate how many theater screens showed the movie by rounding the average revenue to the nearest 1,000. Okay, so we're going to round the average revenue to the nearest 1,000 and then round the final answer to the nearest 100 as needed. And you know, in my math lab, you have to pay close attention to the rounding. Because if you round to the wrong place value, it's just going to mark it wrong as if you didn't do anything right. So pay close attention to those rounding directions. Okay, so first step, we've got to understand the problem here. There's a movie, total revenue, $54 million. That's for all the theaters in the country showing the movie. And now each theater has about $60,289 in revenue. So we need to figure out how many theaters. So we're going to take our $54 million and divide it by that average revenue so we can figure out how many screens showed the movie. Okay, so $60,289 rounded to the nearest thousand is 60,000. Now we have to take 54 million divided by 60,000. So I'm going to need to write out the zeros of 54 million. It's kind of hard to type the word million in the calculator. So then 54 million is 54 with 6 zeros. And when you divide those, we can cross out, just to make life easier, we can cross out 4 of those. And so we end up with 5,400 divided by 6. Now, if you want to type all the zeros into your calculator and not do the crossing out like I did, that's okay. Get the same answer. So when we divide, we end up with 900. So in this case, there's no need to round the final answer because I know the directions told us, let's see, in the directions it says round the final answer to the nearest 100 as needed. But in this case, we didn't have to round to the nearest 100. We just ended up with 900 as our answer. Sometimes that happens, okay? And then we need to look back and check. So we came up with the plan of what we're going to do, how we're going to round and divide. And now we carried out the plan, and we're going to look back and check. Does 900 seem reasonable? Does it seem reasonable that there would be 900 theater screens in the country showing a movie? Yes, it does. It seems like a reasonable answer. It seems to check in the situation. So we're going to go with the answer 900. Okay, let's look at another problem. A classroom contains an equal number of boys and girls. If 15 girls leave, twice as many boys as girls remain. What's the original number of students present? Well, in this case, it would be helpful to use a variable. And when you use a variable, you always need to figure out, what is my variable going to be? What is it going to represent? Because you don't just want to throw X in this situation and not know what X is. So it looks like I'd like to have X be the total number of students present before anybody leaves. It's just however many students are in the room. Now, since half the students are boys, then X divided by 2 would be the number of boys. Same reasoning, with the same reasoning, the other half of the students are girls. So we could say X divided by 2 is also girls. So before anyone leaves, that's what we have. Half boys, half girls. So X over 2 boys and X over 2 girls. And after 15 girls leave, well, I just take my X over 2 and subtract 15 for girls. So after they leave, that's what we have, X over 2 minus 15. We're also told that the number of boys is twice as much as the number of girls. Like after they leave, after this happens, the number of boys is twice as much as the number of girls. So that tells me that boys equals 2 times the number of girls. So that basic, this equation right here gives me something that I can use to come up with an answer. Gives me a framework to work with. So I can put the expression for boys and girls in this equation. See, I have boys here equals 2 times girls. And so I wrote out my equation. Now I can go ahead and solve. When I distribute the 2, that gives me X minus 30. And then multiply everything by 2 to get rid of the fraction. Gives me X equals 2X minus 60. Subtract 2x from both sides means that negative x equals negative 60, so x is 60. Now, x is the original number of students present, and the question is asking for the original number of students present, so it looks like the answer is 60 students. Now we have to check our answer, see if it makes sense. If we have a total of 60 students, that means we had 30 boys and 30 girls. And after 15 girls leave, we have 30 boys and 15 girls. So that there's twice as many boys as girls does hold true. It does make sense. So it looks like the answer is 60 students makes sense in this problem. Okay, let's take a look at another problem. You have 3 alarms in your room. Your cell phone alarm is set to ring every 30 minutes. Your computer alarm is set to ring every 20 minutes. And your clock alarm is set to ring every 45 minutes. If all 3 alarms go off simultaneously at 12:34 p.m., when is the next time they will all go off simultaneously? Okay, so we have 3 different things going on. Remember that first step here, we have to understand the problem. We have 3 different alarms going on. And one is a rotation of 30 minutes, one is a rotation of 20 minutes, and one is a rotation of 45 minutes. So every 30 minutes, the cell phone goes off. So from 12:34, we go ahead 30 minutes, it rings. Another 30 minutes ahead, it rings. Another 30, which is 60 minutes ahead. And then another 30 minutes ahead, it rings, which is 90 minutes ahead, and so on. The computer rings every 20 minutes. So at 12:34, it goes off. 20 minutes later, it goes off again. 40 minutes later, it goes off again. 60 minutes later, it goes off again, every 20 minutes. And then the clock alarm goes off every 45 minutes. So at 12:34, it rings. 45 minutes later, it rings again. 90 minutes later, it rings again. 135 minutes later, it rings again. So if we take a look at what this looks like, I have a list going. The cell phone will ring again in 30 minutes, and then again in 60 minutes, and then again in 90 minutes, then again 120 minutes, because this is for every 30 minutes. It's going to go off. Then for the computer goes off, well, in 20 minutes, then in 40 minutes, then in 60 minutes, then in 80 minutes, because that's on a 20-minute timer. And the clock, well, it'll ring in 45 minutes, and again in 90 minutes, and again 135 minutes, and so on, because this is on a 45-minute timer, okay? So it looks like we need to find the least common multiple between 30, 20, and 45, because really if you look at the list, these are multiples of 30, these are multiples of 20, these are multiples of 140, of 45. So if we list out the multiples and we find the least common multiple, we can see how many minutes pass before they all go off again. Well, here's the multiples of 30, multiples of 20, multiples of 45, and I just kept listing for a while. Like, I wasn't really sure exactly where to stop in my list. I just kept going, hoping that what I wrote was enough, and eventually there would be something that all 3 of them have in common, and then I could stop there. So, I mean, I stopped here at 420, but you could keep going there, for instance, but it doesn't look like I needed to, because I noticed 180, 180, 180. It's 180 minutes that all 3 of them would go off again. So it takes 180 minutes later, which is the least common multiple between all 3. So all alarms will ring simultaneously 180 minutes later. Well, what's 180 minutes after 12:34 p.m.? 180 minutes is 3 hours. So if you add 3 hours, that's 3:34 p.m. Now this isn't I just want to clarify, this is not the only way to solve this problem. It's the way I solve this problem. You may have a different way to solve this problem. It may be easier, it may be harder, but that's the thing with problem-solving techniques, and is that you devise a plan, you carry out the plan, you check your answer, but there's nothing that says that your plan has to be better than somebody else's plan for it to be any better of an answer. You can arrive at the same answer using different plans, okay? This is what I chose to use because I noticed I was listing multiples. And the fact that it was 1234, that they all went off, I really didn't use to the very end of the problem because I just needed to see when they would all go off again later on, how many minutes would need to pass. Okay, so as we wrap up, I just want to, again, state that we spent the first half of this webinar doing inductive reasoning, and then the second half we looked at Polya's method of problem solving. Now I'm taking a look in the chat box, and I don't see like questions related to what we were talking about tonight. I'd like to know if you have any questions. You can go ahead and type them in the chat box. If there's something that you'd like for me to clarify before we wrap up for this evening, if you click on the chat, there's a little, it looks like a little bubble, and it says chat. Okay. Let me see, looking in the chat box, just make sure. Okay. Well, I would like to also clarify that this is my little disclaimer, okay? The webinar is not okay, I don't know what happened. I got disconnected momentarily, I think. Okay, so my little disclaimer is that this webinar was meant to cover on a lot of different topics and help with some things that that normally give students trouble, but it's not meant to be, an all-inclusive. You're still expected to watch the videos in my math lab and read the textbook. This is being recorded, so I will send out the recording to all the MAT 115 instructors along with my notes, and I will also, if you have me as your instructor, I will be emailing out the recording and my notes tonight. So you will be able to watch this again. Some of you are asking if you'll be able to watch this again. You absolutely will, because this was recorded for that purpose, and I will make the record as soon as the recording is available this evening. I will be sending it out to all the MAT 115 instructors to be passed along to all of the MAT 115 students. And it is good to watch the video, because then you can do things like have my notes right there that you're looking at, and you can pause and write things down, and you can go back and rewind, and so that can be helpful to you. My email address is on the screen, ckhouston1@liberty.edu. So if you would like to email me any questions, then let me know. Let me just look real quick again in the chat box here. Let's see. Kristen, there's a Kristen who says that she keeps asking me questions. The star for the multiply symbol. My math lab normally likes for you to use the multiplication symbol. That is and there's a toolbox next to the problem where you can click. It'll have like the fraction symbol, and it has a bunch of other symbols. And my math lab likes for you to click on the multiplication symbol in the math toolbox to mean multiply and not the star. So I have not had luck with the star symbol for multiplication. Okay, someone's asking about going over the 2 to the 4,000. Yes, I can go back and just summarize that, the 2 to the 4,000. Okay. So we need to find the ones digit of 2 to the 4,000. And so the ones digit is the number that's to the furthest to the right. So if we take a look at this, the ones digit would be the 6, 2, 4, 8, 6, 2, 4, 8, 6, so on. And we're trying to do 2 to the 4,000. And you can't type that in your calculator to figure out the ones digit because it's not going to fit on your calculator screen. So we're going to look at a pattern, and if you notice there's a 2, 4, 8, 6 pattern that happens. When you just look at the ones digit, you're not looking at the entire number, but you're just looking at the ones digit. There's 2, 4, 6, 8, 2, 4, 8, 6, 2, 4, 8, 6, and so on. Now, how can we determine, of course, this keeps going, 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6, and so on. Where does this 2 to the 4,000 end up? Well, I'm just going to pick, like, this number, for instance, okay? My exponent is 12. If I divide by 4, I get 3 with no remainder, 0. 12 divided by 4, I'm dividing by 4 because the pattern has 4 numbers in it. Now, if I take a look at this, that exponent is 8. 8 divided by 4 is 2 with, again, remainder of 0. If I take a look at this, my exponent is 4. 4 divided by 4 is 1 with remainder of 0. So notice here that my last digit is 6 for all of those. The 2 to the 4,000, if I take 4,000 and divide by 4, I get 1,000, remainder of 0. So where does the exponent of 4,000 land in this rotation of 6, 2, 4, 8, 6, 2, 4, 8, so on and so on? Where does the exponent of 4,000 land in all of, because that's just going to keep going and going and going? Well, 4,000 also has, when you divide by 4, gets remainder 0. So when it gets remainder 0, that means it's going to fall in, it's eventually going to be in that part of the pattern where the last digit is a 6. Because all of these, 4 divided by 4, remainder 0, 8 divided by 4, remainder 0, 12 divided by 4, remainder 0. So this is telling me that my exponent is part of the remainder 0 part of the pattern. If you notice this, 5 divided by 4 has remainder 1, 9 divided by 4 has remainder 1. Notice the remainder 1s, the last digit is a 2. If we go another step here, 6 divided by 4 is remainder 2. 10 divided by 4 is remainder 2. Notice the remainder 2s have a last digit of 4. So we're just taking a look at the exponents and dividing by 4 because the pattern has 4 numbers in it, and the remainder tells me which part of the pattern I'm in. And so my exponent of 4,000, I'm in the part with remainder 0, so the last digit is a 6. Okay, so I hope that summary helps. And I'm checking the Q&A box real quick. And see. Asked about the multiply symbol. Okay. So I think I addressed the whole pattern with the exponents. There was a question about that. And it will be recorded. I'm going to pass that out. Okay. Let's see. Okay. So I think I've touched on the questions that I could see in the chat box in the Q&A. So if you have any further questions, please don't hesitate to send me the email to ckhouston1@liberty.edu. And I'm also going to be emailing my presentation to all the MAT 115 instructors, as well as the recording will be made available as well. So I want to thank you all for this evening, and I pray God's blessings as you continue in Module 1 of this week. And have a good evening. I'm going to go ahead and stop the recording.